All right, grade 12s. Today is, of course, the 17th of March. And I know we are recording, and this is going to go live on, or not live, but it's going to go post on YouTube. We probably will look to end this class today a little bit early because I am about to go into load shedding at 8 o'clock. I'm scheduled for load shedding at 8 o'clock. So I'll probably end just before then, just in case somebody at the plant or whoever controls the switch gets a little fingers itch a bit too much and gets trigger happy, and then boom, flips the switch like 5 or 10 minutes early. Okay, so I just wanted to let you all know that I'll be ending slightly earlier than on the hour because I don't want to just disconnect with regards to load shedding. Okay, well, today, guys, I'm going to introduce you grade 12s to something else in organic chemistry that's called addition, elimination, and substitution reactions. Okay, so let's get our heading down. Okay, in organic chemistry, these three reactions or categories of reactions do take place. Okay, and as we well know, we have been chemistry students for a while now. Okay, so we do know that chemistry, or the foundation of chemistry, is based on reactions. Okay, not just in organic chemistry, but we've possibly dealt with some organic compounds, chemical formula in grade 11 and in grade 10 already. Okay, so we are again, in organic chemistry, besides learning now how to name them, the homologous series, how they are formed, how to draw them, the different types of isomers, right, the different types of ways we can represent them. Okay, structural formula, condensed structural formula, of course, chemical formula. We've learned the general formula as well. So all those things, now we need to learn the reactions that do take place. And it's funny because in organic chemistry, there are three categories called addition, elimination, and substitution reactions, but underneath each category are different names for the different reactions that do take place. Okay, so what we're going to start with first is, of course, the addition reactions. Okay, almost like in BODMAS. Okay, addition comes before subtraction. Okay, so let's start with addition. A little bit of grade 5 maths coming through there. Wasn't so long ago for me. Okay, addition reactions. Okay, now addition reactions, okay, happen to these types of hydrocarbons. Usually happens to unsaturated hydrocarbons, and among those unsaturated hydrocarbons are alkenes, okay, alkynes, all right, as well as I was attempting to draw the ampersand there, as well as cycloalkenes, okay, which I've not seen in an exam in a few years. Okay, I've not seen a structural formula organic compound drawn or given in a long time. Okay, but nonetheless worth mentioning. Okay, like I mentioned, they're unsaturated. Okay, so let's put that in there. And they are hydrocarbons, and so an alkene, an alkyne, all right, they only consist of hydrogen and carbon atoms. Okay, and they undergo addition reactions. Okay, and i.e., that's a reaction in which the double or triple bond will be broken, so that new atoms can be added to the molecule to form a more saturated product. Okay, and the first type of addition reaction that we will discuss is something called halo, genation. Okay, to say it fast, hydrohalogenation. Okay, that's the first type of addition reaction. Okay, now what does this consist of? This consists of a hydrogen halide. Okay, a hydrogen halide that is being added. Okay, an example: hydrochloric acid, HCl, hydrogen bromide. All right, HI, not high, okay, hydrogen iodide. All right, and it obviously gets added to what? Plus an alkene. All right, to break the double or triple bond, all right, but in this case to an alkene, to break the double bond and to form a saturated compound or a more saturated product. Okay, what forms after you add a hydrogen halide, all right, which is a hydrogen plus a halogen, to an alkene? You get a haloalkane. You get a haloalkane as a product afterwards. Okay, which is like pretty cool. Okay, so if we have a little example, okay, if I have ethene, so I'm going to draw it in structural formula, the double bond there, and just draw the little arms. In Australia, they'll be called arms. I love Australian. I don't ever think it's an accent. I think it's a language on its own. Anyway, but that's just my thought. Sorry for any Australians that's going to watch this video. And let's add HBr. Okay, showing the single bond between them. Okay, a haloalkane is going to form. So we just basically show that this double bond breaks. So now if it breaks, we have a single bond between the two carbon atoms. Okay, we have a hydrogen and a hydrogen, hydrogen and a hydrogen, and we have a hydrogen and a hydrogen, and here our bromine will be situated, and the rest would be hydrogens. Single arms. Okay, and the name for this IE will be bromoethane. Now, grade 12s, there is such a thing here in hydrohalogenation called Markovnikov's rule, all right, which basically states that in compounds where the double bond is isometrically placed in the molecule, as we see here, it's isometrically placed, the major product is formed by the addition of the hydrogen atom to the carbon atom that already has the most hydrogen atoms, and the addition of the halogen atom to the carbon atom with the most alkyl substituents, okay, which is the case here with our next example, and I'm going to show you how Markovnikov's rule actually applies. So in the next example here, I'm going to make use of prop-1-ene, okay, so I'm going to take prop-1-ene, which we know has propene, or prop means 3. So prop-1-ene, I've got a hydrogen on top here, a hydrogen over here, and I've got one hydrogen here and nothing on the second carbon, and a hydrogen, actually 3 of them on the last carbon atom. Okay, and I'm going to react hydrochloric acid with it, so I'm going to react HCl. Okay, what's my product? Okay, now Markovnikov's rule said that the hydrogen atom will go to the carbon with the most hydrogen atoms, all right, the most hydrogen atoms on it. In this case, where the double bond is, in this part here, the carbon that has the most hydrogen atoms on it, bonded to it, is the first carbon, right? It is the first carbon. So what do? We put the hydrogen on the first carbon, and the chlorine will go to the second carbon. So it'll look like this. Still get a haloalkane. There's the top one, there's the bottom one, and here's the one that we just added. Okay, and the chlorine will go at the bottom here because there the hydrogen was already there, and then these 3 hydrogens stay the same. Okay, so we see this is the hydrogen, maybe I'll put this here, this is the hydrogen that got added, and there's the chlorine that went to the second carbon, and the hydrogen went to the first carbon because there was the most carbon atoms, or the most hydrogen atoms on the first one. So that's how Markovnikov's rule works with hydrohalogenation. You add the hydrogen to the carbon atom with the most hydrogen on it already. Okay, so that would be to name this. How would we name this? And anybody give me a name for this product? Now the next addition reaction that takes place, okay, there's only about, let me see, that was the first one. We have 2, 3, 4. Okay, we've got another 3 to go for addition reactions, and then we're on to our elimination reactions. Okay, so the next one, number 2, is just the second part of the first part. It's just halogenation, okay, which I'm sure we all, via inquisitiveness, if that's the correct term, but intuitive was right, I'm not sure if inquisitiveness was right, but anyway, is just the addition of a halogen. We just add in a halogen. Alright, so example, halogens don't exist on their own, so if X2 is the, X is the placeholder for halogen, X2, so example, F2, which is fluorine, iodine, of course, bromine, and chlorine. Okay, we know halogens don't exist on their own, they have to be bonded to another one of themselves. Alright, and what is formed? Okay, a haloalkane. Right, a haloalkane as well. But we also add this, or the halogens, we add them to an alkene as well, as we can see. The only time we can form a haloalkane is when we add it to an alkene. Okay, the double bond between the carbon atoms obviously break, and a halogen atom attaches to each of the carbon atoms. So if we must take another example, if we must take ethene again, okay, and we can still, we can just, I'm going to draw it slightly different. So ethene, I'm going to draw it like this, and I'm going to draw it like this. I'm just drawing it slightly different, so I can show you that this bond is going to break. And what we're going to do, we're going to add that to Cl2. So chlorine bonded to chlorine. How's that going to look? Well, that's still going to stay the same. That's going to stay the same. This changes. The double bond breaks. That hydrogen stays. That hydrogen stays. That hydrogen stays. And here we insert, those lines are not straight, so give me a second. That still wasn't a good straight line, but anyway, I'm not going to worry about it now. We insert our chlorine atoms. Okay, Cl, Cl. And of course, we call that 1,2-dichloroethane. Okay, because it's on 1 and 2. Okay, 1, 2 dash dichloroethane. Remember, there's 2 of them, so we have to add in our prefix, di. Okay. So this one is pretty basic. This one's pretty simple. The same thing would happen if it was another type of halogen, but this one is pretty simple and not much can be further said about it. This is just how it is. We have a third one, number 3, which is hydration. Okay, now we've all heard this term before. We've all been using this term for years. Okay, hydration. Okay, this is addition of water, right? H2O. Okay, it's addition of water, but more specifically, it's addition of water to an alkene. Okay, most of these addition actions, as we can see, are all addition reactions to alkenes or alkynes. Okay, so the double bond would break between the 2 carbon atoms, and 1 hydrogen would go to one of the carbon atoms, and then another OH group would attach itself to the other carbon atom. Okay, and this reaction is used in the industrial, right? The industrial prep of alcohols. Okay, just thought that's a nice little did you know little fact there. Markovnikov's rule also applies here. Okay, the major product that forms by the addition of the hydrogen atom to the carbon atom that's at the double bond with the most hydrogen atoms. Okay, so still Markovnikov's rule applies here. Okay, so let's take propene again. Let's take C double bond carbon here, single bond, and here we've got the hydrogen and the hydrogen, 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 and hydrogen. And let's react that with H2O, and water we know is a bent molecule, which looks like this. Okay. What we do here is this reaction also has reaction conditions. Okay. Back with hydrohalogenation, reaction conditions were that it was water-free hydrogen halides. Okay, that there can be no water present in the reaction, otherwise we'd have an OH bonding to one of the groups. Halogenation is spontaneous, and hydration, reaction condition, is that an excess of water and a strong acid such as sulfuric acid, so we use H2SO4 as a catalyst to speed up the reaction here, to get rid of excess water. Okay, now watch this. Okay, react that with water. Now again, one of these hydrogens here is going to break off and going to go to the carbon with the most hydrogen atoms at the double bond. So it's going to fill up this space over here. And here we're still left with the OH group here that's going to attach itself to this carbon. Alright, so we'll end up, if I change the color to CH3, so we'll have 3 hydrogens on the first one, single bond, the hydrogen will stay here, and then we'd have the OH group attaching itself over here. The third carbon remains unchanged. Okay, and if we had to name this compound now, we can clearly see that it is propan 2-ol. Okay, propan 2-ol as the major product that is forming in this reaction. The final addition reaction is called hydrogenation. Okay, it's the fourth one, hydrogenation. Okay, hydrogenation is only the addition of hydrogen. Okay, we just add in hydrogen to an alkene. Okay, that's all. Okay, we do this to saturate the product, so a more saturated compound or saturated product is formed. Okay, reaction conditions for this reaction though is that there's not many, but a catalyst is used, all right, such as platinum, PT as a catalyst, or nickel, all right, as it provides a surface where the reaction can take place. And of course, we know what a catalyst does from grade 11 physics, or chemistry rather. It decreases the activation energy. So if we take propene again as our example, okay, there we go. And we're just going to add it to hydrogen, and then we know hydrogen does not exist on its own, so we add in it to H2, so it's plus H bonded onto another H. Okay, and what forms a saturated product, which is known as an alkane, of course, because the double bond is just simply going to split. Okay, Markovnikov's rule doesn't really apply here, as we just add in hydrogen, so it doesn't matter which hydrogen goes where, to be honest. So we end up with, from propene, right, or prop-1ene, okay, we end up with just propane as our saturated hydrocarbon after just added hydrogen to an alkene. All right, and that's the final addition reaction that does take place in organic chemistry. Right, elimination reaction is the next type of reaction that does take place, but let's first talk about what it is. Right, the elimination reactions consists of basically the elimination of an atom or group of atoms from a saturated molecule. All right, so these take place in alkanes, haloalkanes, and alcohols. Okay, which again, I must say, involves the elimination of an atom or group of atoms. Okay, I'll just write of an atom or group of atoms from a saturated molecule, such as the above. Okay, and the first one that we are going to look at is very similar to the first one of addition, but we just add a little prefix in front of it, dehydrohalogenation. Dehydrohalogenation. Okay, now I'm sure we can all figure out this. So if we dehydrohalogenate, all right, that's not a real word, but I'm just saying, if we're basically going back to what the compound or the molecule that we had before we had the hydrohalogenation addition reaction. Okay, so we're going back, of course, to an alkene of some sort. Okay, that's just pretty basic to and intuitive to understand. So we'll take away a hydrogen halide. Okay, so we are taking away a hydrogen halide. So we're taking away HX. Okay, which is basically the general the general formula of a hydrogen halide, because X stands for a halogen, so HCl or HBr, etc., etc. Okay, that's what happens. Okay, and the product that forms, of course, is an alkene. So like I said, when we go backwards, okay, when we went from an alkene to a haloalkane, it was hydrohalogenation, right? And of course now we're going backwards. Okay, when we have dehydrohalogenation or in elimination reaction, there's something that's called Zaitsev's rule. All right, and that rule is that if more than one elimination product is possible, the major product is formed when the hydrogen atom is lost from the carbon atom already with the least number of hydrogen atoms, which I will obviously explain right now. Or another way to say that, the major product is the alkene with the highest substituted double bond. In other words, the least hydrogen atoms and the most alkyl groups on the carbon atoms of the double bond. The best way to demonstrate Zaitsev's rule is to actually draw it out in structural formula. Okay? Excuse me, guys. Which I'll do in just a moment. There are some reaction conditions, okay, and you need to use a concentrated solution of sodium hydroxide or potassium hydroxide, all right, in pure ethanol as a solvent. So in other words, if you want to eliminate anything, dehydrohalogenate anything, or go through an elimination reaction, you must react your haloalkane with either a solution of sodium hydroxide or potassium hydroxide in pure ethanol. Okay? And heat is applied under a reflux. In other words, gases condensate, and then they return to the reaction during heating. So a lot of heat will be given off as well. So almost as if it is an exothermic reaction. Okay, because it does heat up, of course. So to demonstrate that, okay, which it can be examinable, but I doubt they would ask it in that depth. But they sometimes will ask for a reaction condition of a certain reaction. Okay, they could be spiteful and do that. Okay, but let's think of a compound. Let's think of butane. I like butane because I'm tired of prop. So let's take 2-bromobutane, CH3, Br. Obviously CH is over here as well, and we got CH2 and CH3. Okay, so here with Zaitsev's rule, okay, basically if more than one elimination product is possible, so we're going to eliminate, of course, the hydrogen and the halogen and the bromine. Okay, if it's possible, the major product is formed when the hydrogen is lost from the carbon with the least number of hydrogen atoms. So let's count here. The first carbon has 3 hydrogen atoms. The second one has 1 and a bromine. The third one has 2. And the last one, which is the fourth one, has 3. So which carbon has the least hydrogen atoms? The second one. So the double bond is definitely going to form here. We need to react that, of course, with concentrated NaOH. I'm going to write conc for concentrated NaOH in pure ethanol. This is a reaction condition, and I need to write it down. All right. Now, what forms? Remember, we're taking away the hydrogen, and we're taking away the bromine. Okay, that's going away. Bye-bye. Cheers. Okay. The major product that is going to be forming, okay, is obviously going to be forming on the second carbon. So the first one will remain unchanged because that had 3 hydrogens, so nothing happened there. The second one, there's a double bond, so I only have 1 carbon, or 1 hydrogen can fill that place. 1 hydrogen can fill that place. All right. Another hydrogen can fill that place, of course. And we have a carbon with 3 hydrogens at the end here, which is the major product formed. Okay, I might have gotten a little mixed up in my explanation, so let me just re-explain that again. Although we took away a hydrogen and a bromine, we took away the bromine actually from this one, and then we just took another hydrogen over here, and we left this one over here. Okay, just for how I've drawn it. So let me just fix my little explanation there. I made a mistake. Apologize. Cool. So now we can see where we have disappeared from. Okay, to get this type of molecule, which is, of course, butene. And I've also drawn it in the wrong place. Jeepers. Is my brain fried, or am I just having a bad day? Okay, it should be drawn over here. Butene. And of course, some byproducts are formed, of course, such as, where does the halogen now go to? Of course, it becomes NaBr. Okay, because remember we reacted it with sodium. Okay, so the halogen will go to the sodium, NaBr, sodium bromide, plus, and we had OH from the hydroxide that now bonds to this other hydrogen plus H2O. And that's dehydrohalogenation. Okay, but the major product is actually what they're asking for anyway when they give you that diagram that I think Mr. Ravens you might have seen today. Okay. The next one we're going to go through, of course, is one that we're quite familiar with because we used it more than once or twice in our lifetime, is dehydration. Okay, it's a real process and a real thing that actually happens. But dehydration, of course, I'm sure we understand, is the elimination reaction where water H2O is eliminated. Okay, we're taking away, couldn't even spell eliminated. I'm definitely having a bad day today. Eliminated. Okay, from an alcohol. Okay, it's taken away from an alcohol. So we don't just take away the OH group, but we take another hydrogen with it as well. Okay, this is the reverse reaction, of course, of hydration. Okay, we add water in a preparation to an alcohol. Okay, we add water to an alkene to form an alcohol. Okay, now we're taking water away to go back to an alkene. Okay, like I said, we take away the OH group together with another hydrogen atoms. Okay, sorry. The reaction cannot take place with methanol, all right, as it only has one carbon atom. So there's no adjacent carbon atom that can release the hydrogen atoms. So unfortunately, methanol, which is just one carbon with 3 hydrogens and 1 OH group, this reaction can't take place. You can't dehydrate it. You can't go back to an alkene because there's no additional carbon atom there to even form a double bond. In the case, if we have a look at the reaction conditions, okay, we definitely use a catalyst, or we use concentrated sulfuric acid or phosphoric acid, all right, when we heat the alcohol together, all right, to get this reaction to break off. Okay, so if we take ethanol, because it can work with ethanol, so let's just draw ethanol quickly. C, it has 2 carbons, hydrogen, 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 another hydrogen, and an OH group. Okay, so what's going to happen is that, of course, the OH group, that's going to say bye-bye, and also one of these hydrogens, I'll pick that one, is also going to go. Okay, like I said, that reaction takes place with concentrated sulfuric acid, so H2SO4 with a little triangle there. And of course, like I said, we go back to what we had before, which of course is just ethene as the major product that is formed. Okay, and of course, if we take away an OH group and another hydrogen, they will bond to each other, which will obviously be H2O. So I'll draw it in structural formula. OH. Okay, and that is dehydration. All right, and it is definitely asked a lot in those flow diagram questions. Okay, then there's a third one that's worth mentioning, which is cracking of hydrocarbon. All right, cracking. Okay, now cracking is something you're welcome to do your own research on. Okay, I've never seen it in the exam, but I have seen it only once. Okay, where cracking consists of when you take natural crude oil, which consists of very long carbon chains, okay, with high molecular masses and high boiling points. All right, it makes you can't really use it in the fuel industry. Okay, so the longer the alkane chains can be broken up into more useful or shorter carbon chains. Okay, smaller molecules. Okay, this process is called cracking, breaking up long alkane chains into smaller alkane chains. Okay, because shorter chains burn more evenly and easily. Okay, so that's the cracking of hydrocarbons process. Okay, called it cracking. Now, what forms as a result of this? The products, okay, that can form are alkanes, all right, as well as alkenes. Okay, but they have much shorter carbon chains. Okay, or if the alkenes form, when they do form, it'll be plus H2 gas at the same time. Okay, I'll bracket this. Okay, Cracking can occur at certain conditions, okay? Thermal cracking, which is under high pressure and high temperatures, okay, where there's no catalyst. But sometimes we will have a catalytic cracking, okay, where we'll add a catalyst, which is PT on the periodic table, okay? If we have a look at some examples quickly of cracking, okay, let's say we want to crack ethane. Okay, so let's crack ethane. We want to shorten the carbon chain. Okay, cracking ethane happens at 800 degrees Celsius in the presence of a platinum catalyst to form ethene plus H2 gas. So if I want to crack ethane rather, so I want to break it up into something that can burn more easily. So the general formula or the molecular formula is C2H6. If I react that at the temperature or crack that at a temperature of 800 degrees Celsius using a platinum catalyst, I will get C2H4, which is ethene gas, plus H2 or hydrogen gas. Okay? Let's take another example. Let's say we want to crack or look at the cracking of butane, which we know is a 4-long carbon chain, okay, or 4-carbon chain, okay, which we know butane, of course, is CH3, CH2, CH2, CH3, okay, condensed structural formula. So let's crack the CH3 to the CH2 bond. Let's crack that bond. Okay, let's crack that. Okay, so we'll end up, if we use a catalyst, if we crack that, we'll end up with, of course, CH4, which is methane. Okay, we crack that CH4 plus, and then you'll have your CH2 double bond CH, of course, because I cracked it, and one hydrogen also went away. CH to CH3, which is now propene. Okay, so we are breaking up the longer carbon chains, break them up into smaller carbon chains. We can even break up something called decane. Decane is a 10 carbon chain. Okay, a carbon chain with 10 carbons. Okay, we can break that up even into ethene and octane, breaking it up, making the carbon chain smaller. Substitution reactions. Okay, now a substitution reaction is the substitution of an atom or group of atoms by another atom or by another group of atoms. So essentially we are swapping an atom or group of atoms out for another group. Okay, that's all we're doing. Okay, so when you replace an atom or group of atoms with another or a different atom or group. Okay, that's all it is. Okay, so let's first look at the substitution reaction that occurs, all right, in the first group, which is having a look at the halogenation of an alkane. Okay, so that's what it's called. Okay, the first one, it's the halogenation of an alkane. Okay, and then the next one will be haloalkanes. So let's go have a look at the first one. I want to use a different color. I want to use orange a bit. Halogenation of alkanes. Okay, so now alkanes are not very reactive, okay, because they have a single carbon-to-carbon bond as well as a single carbon-to-hydrogen bond, which means they are fairly strong and they're also fairly stable. Okay, they have non-polar bonds, and they do not readily react with other polar molecules. In other words, they don't really react with water, they don't really react with hydroxides or bases, or even acids, as we see, because there's a straight chain. There's no room, or hardly any room, for any type of reactions, okay, to take place. Okay. But they do react with halogens, though, all right, with the addition of energy, okay? So if I have, for example, methane, okay, methane, I'll write the name first, methane, and I want to react that with chlorine gas. Chlorine gas. Okay? I need to obviously get a certain product. Okay? So let's talk about it. Let's figure it out. So let's say I have methane, CH4. Alright? CH4. And this is methane gas, of course, plus chlorine gas, which is Cl to Cl. Okay? And we want to get a product that's obviously formed. Now, what's happened is here we are going to just swap a hydrogen and a chlorine. Alright, that's all we're going to do. We're going to swap them. So in other words, hydrogen is going to take the place of chlorine in the chlorine gas, and chlorine from the chlorine gas is going to take place of the hydrogen in methane. Okay, so what do we have? The name, or let's actually draw it first. That hydrogen will stay, that hydrogen will stay, this hydrogen will stay, and we'll have a chlorine bonded onto it plus HCl. Okay, so the name of the major product would be chloromethane. Alright, so that's the halogenation of alkanes. In other words, we're just substituting a hydrogen for a halogen atom. Alright, that's all. Okay, and of course that can of course, if we react it once again, so if we react chloromethane, all right, with chlorine gas again, okay, then we can essentially get rid of another hydrogen atom. Okay, we can continue doing that. Okay, we can continue doing that. Okay, the more we react it, the more the substitution just takes place. Okay, that's all. Okay, that's all that happens. Hydrolysis, which is the process of going from a haloalkane to an alcohol, okay, which you take in two saturated compounds, okay, and you react them together, okay. So this reaction usually happens, all right, in the presence or hand in hand with a strong base. Okay, this goes hand in hand with a strong base, okay, such as a diluted sodium hydroxide or potassium hydroxide. Okay, potassium hydroxide or sodium hydroxide are very strong bases. Okay, they're very strong. Okay, so what will happen here is that the halogen atom in the haloalkane will be easily replaced by another functional group. In, for example, OH. The OH functional group will easily replace the halogen in the haloalkane. Okay, so let's take the example. Let's take chloroethane. All right, chloroethane. Here's my chlorine, and the rest are all hydrogens. Okay, let me add them in. Okay, and we're going to add them to, let's use, oh, don't know what that line came from, NaOH. Okay, let's use NaOH. Okay, now what's going to happen here is that the halogen, chlorine, and the OH group here are going to trade places. Okay, the chlorine is going to go bond with the sodium, okay, which was 1/2 of the base atoms, and the OH is going to be bonded onto the ethane. Okay, so what's going to happen here is an alcohol is going to be created. Okay, so we have then OH group, which is bonded on here, and I'm sure we all can guess the name, or not guess the name as if we don't know, but say the name, right, or write down the name, which will obviously be ethanol. The alcohol formed, plus one of the byproducts, which is NaCl, so a salt would be formed, table salt in this type of reaction. That's all that happens, that they trade places. Okay, the haloalkane is non-polar, so that won't mix with water in the dilute base. Okay, it must first be mixed, of course, with ethanol, and the reaction will be a heated reaction. Okay, it will be heated. Cool, let me just see. Okay, hydrolysis does in reaction will take place slower with water though than with the base. Okay, so if we just take a quick squizzle at what happens if we took 2-bromopropane in alcohol. So 2-bromopropane. So here's my bromine on the second one. And I'm just going to omit the hydrogens for now, just draw the branches. Okay, obviously you know hydrogens go there. Plus...
No, I'm just saying, you must ask me nicely and I must answer it nicely.
Plus water, so if we draw water in a structural formula, it's a bent molecule. Okay, so now we're taking the same reaction. I might as well just add the hydrogens in here because it just looks a bit ugly. There you go. Alright, and what the reaction is going to form, it's an alcohol will be formed. It just reacts a bit slower than with the base. Okay, so you'll end up with propan-2-ol. Okay, so obviously the bromine will trade places with this OH group over here, and then we'll bond with this hydrogen over here. So there's the OH. Okay, and that's the hydrogen. One of the things I hated about organic chemistry was how long it took me to add in all my hydrogens. Anyway, plus HBr, hydrogen bromide. So the major product would be propan-2-ol. Okay, as the alcohol formed. All right. We have one more that we need to go through. Okay, that one was hydrolysis. The third one is now taking alcohols and now going to haloalkanes. Okay, so now if we have alcohols that reacts with a hydrogen halide, so let's say we have, I'm going to use R as the rest of the molecule and OH as the functional group to show you that's an alcohol that reacts with HX, such as HCl, HBr, or HI. They will obviously form haloalkanes. Okay, are the rest of the molecules with all the carbons and stuff, and X being the halogen. Okay, this is now the reverse reaction of hydrolysis. Of the hydrolysis substitution reaction. We are now reversing. We're going from an alcohol back to a haloalkane. Okay, previously we went from a haloalkane to an alcohol. That was hydrolysis. This is the reverse reaction. Okay, so just to demonstrate this in a simple type of reaction itself, let's say I have propan-1-ol. Okay, now don't be surprised if you look at propan-1-ol a little differently here. Okay, I've drawn my functional group on what looks like the long or the last carbon, but remember, with organic chemistry, sometimes reading is not like we read a book, so we don't always read from left to right. Okay, we're reading the carbon with the functional group as propan-1-ol. Okay, if I react that with a hydrogen halide. So I'm reacting that with HBr, for example. What do I get? Okay, something is it's still going to substitute now. The OH is going to substitute with the bromine. They're going to trade places. Okay, so I'm going to get a haloalkane, all right, which is 1-bromopropane. So still going to have an alkane. There's my bromine. Okay, I'm going to leave the hydrogens out for this one, plus the OH bonding to the hydrogen that was available here, so water. All right, so it's basically the reverse, all right, of hydrolysis. Okay, that's all. This third one is alcohols to haloalkanes. It's just the reverse of hydrolysis. That's it. Okay, and that, ladies and gentlemen, is all the reactions that do take place, or the major reactions that do take place in organic chemistry. Okay. And that grade 12 concludes my lecture for today. Thank you so much for joining me on addition, elimination, and substitution reactions. All right. Please stay tuned for the next video. We will look at a few examples in more great detail and how to answer those questions in a formal test or exam setting.